So good morning, everyone. My name is Wolfram Erlhagen. I'm the chairman of this session. It's really a pleasure for me to start the session on dynamic neural fields. All four talks today have in common that they are dealing with an integral differential equation, now known as the Amari equation, named after Shunichi Amari, who already in the 70s proposed and analyzed this equation with the goal to explain the formation of activity patterns in large-scale neural populations of the human brain. Amari is now considered one of the fathers of mathematical neuroscience, a new research area which I think it's fair to say is not yet well represented in Portugal. There exist in other countries really dedicated research centers dedicated to mathematical and computational neuroscience. So this session also serves to make publicity for this new research area. More recently, in the emerging area of neurorobotics, the theoretical framework of dynamic neural fields is also used to endow robots, autonomous robots with human-like cognitive capacities based on processing principles of the human brain. So the talks will show how specific questions from the applied areas, neuroscience and robotics, give rise to new mathematical investigation. So there's really a close link between here mathematics and these emerging areas, neurorobotics and neuroscience. So I will give the word for, or will introduce the first speaker, Veronika Wojcik from the University of Minio, and she presents a novel dynamic field model supporting a continuum of bump amplitudes. So, may start, Veronika.
Thank you. Okay, can you see my screen? And can you hear me?
Yes.
Okay. So my name is Veronika Wojcik, and I will speak about a novel dynamic field model supporting continuum of bump amplitude. Mathematical modeling of neural processes is a very difficult task, and one of the reasons for this is a huge number of neurons in the human brain, and even larger number of connections between them. One of the approaches to model neural activity are neural field models, and they describe the mean firing rate activity in large populations of neurons. Those models are phenomenological. That means that they only account for the firing rate and not for the biophysical details of neural firing. They are formalized by nonlinear integral differential equations, and the most commonly used formulation is the model introduced by Amari in the 70s. This is the equation, and now I will go over each term of the equation. So first we have tau, that is the time scale of the field dynamics. And then U is the activity of a neuron at position X and time t. We don't have this integral term, which is a convolution, and inside there is W, that is a connectivity function that depends on the distance between the neurons and not on the exact position in space. And then we have F, it's the firing rate function or transfer function. So this function converts the activity into firing rate. And we have external localized input to the field. And finally H, which is the resting state to which the field relaxes when there is no input. Here I plot some example of possible choices for the connectivity function and the firing rate function. And localized solutions to those equations are called bumps. Bumps are triggered by external input, and then they are sustained in the field by recurrent excitatory and inhibitory connections. So when the input is no longer present, thanks to those connections, the bump persists in the field, so it is self-sustained. And bumps are input specific, meaning that the position in space of the bump will depend on the position of input, and because of this, they are used to work to model the working memory function. And here I want to show an example of how the bump is created with input. Yes, we apply a short localized input, and then the bump is sustained in the field. And there is also forgetting. So when there is strong negative input applied to the field, the whole activity is brought below threshold, and the field relaxes to the resting state. In the Amari model, the shape of the bump depends only on the connectivity function W. But there is large evidence that this is not sufficient to explain the pattern formation in neural tissue. And there is large evidence that the shape of input-induced pattern still preserves some characteristics of the input that created it. And we address this issue by introducing our new model. The model looks like this, and we created it by coupling together two fields of Amari type with activities U and V. And if you look on the first equation and ignore the input from V for a second, you see that this is just pure Amari model. So all the terms are the same. And then to this Amari field, we couple second field that looks very similar, but the difference is that the convolution term is taken with a minus sign, and we take the activity of U, also the convolution term here. And this formulation gives us the solution. We have like a bump solution in the first field and like inverted bump in the second field, thanks to this minus sign here. And for the work that I present today, we use Heaviside step function for the firing rate S. So the output of F is either 0 or 1. And for the connectivity function, we use Mexican head kernel that is given by difference of two Gaussians. And the initial condition is given by formula here. And later I will explain how the choice of K affects the behavior of the model. Here we have a comparison of some solutions in the Amari model and in our new two-field model. So in the first example here on top, I show the results of applying two inputs where one input was stronger than another. And in the Amari model, both resulting bumps are exactly the same because the shape is defined by W. And in the two-field model, you can see that the amplitudes are different. And here the amplitude of the bump depends on the amplitude of the input. And in the second example, I apply two inputs, but one of the inputs has bigger width. And you can also see that the result in the two-field model are the two bumps in which one has larger width than another. In Amari, again, we have two bumps that are exactly the same. And we analyzed our model both analytically and numerically. So we first used the linear stability analysis, and here the initial condition is that the sum of both populations is equal to the constant K. And we linearize the system around the steady state and look at the eigenvalues of the system. And I don't want to bore you with calculations, so I just show the result. And the first result is the condition for existence of a bump, which looks like this. And here, delta is the width of the bump. Theta is the threshold for the firing rate function. And capital W is the integral of the kernel. And there are at most two values of delta that satisfy this condition, meaning that for a given value of theta, we have at most two bump solutions. And we then look at stability of those bump solutions. And so the bump of width delta is stable if the W of delta is more than 0. And W is, again, our connectivity function. And here I plot the existence and the stability of bumps. So we have here a bump with delta is a function of theta. And you see that the bump solutions come in pairs. So we have the branch of wider solutions and branch of narrower solutions. And as theta increases, they annihilate in the saddle node bifurcation. And looking at the stability condition, we know that the bumps with larger delta, those on the upper branch, are stable. marked by solid line, and those in the lower branch are unstable. And typically on the bifurcation diagrams, I will always mark the stable solutions with solid line and unstable by dashed line. And here I show the example of one pair of solutions for one value of theta. So we have in black the wider solution that is stable, and in gray the solution was very small with delta that is unstable. We then analyze the model numerically, and for this we use Newton GMRS solver, and we continue the solutions with the Arcang's continuation method. With this initial condition for both fields. So again, the sum of two fields is equal to constant k. In this case, this particular choice of the pattern here doesn't really matter. We just want something localized. But the exact parameter, it could be even like rectangular input. It doesn't affect the shape of the solution as long as this sum of two populations is equal to k. And again, we have a bifurcation diagram. Here I plot the maximum of u, which is the amplitude of the bump as a function of theta. And we can see again that we have two branches of solutions. One branch is stable, second, the lower branch is unstable. And I also show two examples of solutions. And yeah, this shape is the same for any value of theta as long as k is a constant. So this is different when k is chosen to be a spatially complex pattern. So here, which is k to be a Gaussian. And in this case, by changing the parameter of this pattern here, we obtain different bifurcation diagrams. So the shape of solutions will depend on this pattern here. And here I plot two bifurcation diagrams for different choices of parameters here. And you can see that they are very different. So this is one important thing here, that the shape of solutions and the bifurcation diagrams depend on this pattern. And the second important thing is that we have this additional branch of stable subthreshold solutions that do not exist in the Amari model. And those are the solutions of this type. So you have the threshold here, and the solutions are under the threshold, and they are of the form u equals v, and in fact they equal k of x over 2. And this branch just continues as long as I bothered to check for any value of theta. And here I show an example of two-bump solutions, and the bifurcation diagram is very similar. So again, we have stable branch of stable solutions here and branch of unstable solutions here. And again, we have those stable subthreshold patterns. This is an important example because this kind of solution do not exist in the Amari model with the Mexican head kernel. And we analyze the model also in 2 dimensions, both analytically and numerically. And here I show just one example of continuation of two bump solutions in the 2D model. And just to conclude, I want to say that we proposed robust integrator model. And just as the last example, I'd like to show integration of dynamic input. So that's input that changes in time. And I plot here the amplitude of the input and the amplitude of the bump. So you can see that the amplitude of the bump increases with the amplitude of input. But we were interested in seeing if we can have a bump with increasing amplitude, but with fixed width. So we applied input in the form of truncated Gaussian. So the width of the input is limited. And you can see here, I plot the input and the bump width, that the width increases only initially when the bump is formed, but then it stays fixed. And then to just further illustrate this, I have example of two inputs applied in the sequence, and you see that the amplitude increases with each applied input, but the width increases only initially, and then it stays fixed. We applied the model in the area of robotics, and I show 2 examples here. First example is a human-robot cooperation task, and the robot has to learn the order of handing over objects to an operator, and the integrator model is used to memorize and to recall the serial order of handing over. And the second example is a simulated factory floor with an autonomous robot and 2 workbenches, and the robot has to make decision to which workbench it has to go in a given trial. And this decision is based on the accumulated evidence from previous trials, and we use the integrator model to accumulate this evidence. And one of our future goals is to use this to validate this approach in the real industrial environment, because it is more tricky than the simulation. And on the mathematical side, we want to also do the stability analysis for the case when the input is present. And there is also a number of possible extensions to the model, and one possible extension is incorporation of delays. And that's it, I think. Thank you.
Yeah, thank you, Veronica. Yeah, we have maybe, if there is a short question, if not, at the end of the session, I mean, we have maybe more time for questions. If there's not at the moment, so I don't see here in the chat specific question, maybe then we can, or here is one question, maybe.
May I ask?
Peter, yeah.
Just one short question, because I skipped maybe in the start of the talk. What is the physical meaning of theta, the parameter you use for the stability analysis?
So theta is the threshold for the firing rate.
Is a threshold. Okay, okay. I just skipped this this moment. Thank you.
Okay, then we may advance and ask Flora to start her presentation on a rapid learning of complex sequences with time constraints, dynamic neural field model.
Now, can you hear me?
Yes, we hear you.
So my name is Flora. I go to present work that is about a rapid learning of complex sequence with time constraints and dynamic field model. Many of our sequential activities, like playing piano or even adding over objects to another person, require a couple process of the order and timing of events. And our goal is endo-cognitive robots with the capacity to learn complex sequence with time constraints, and by that supporting more natural human-robot interactions. In this presentation, I'm going to present a dynamic near field model for learning a sequence of events with time properties using dynamic narrow fields formalized by nonlinear integral differential equation introduced by Amari and presented by Veronica in the previous presentation. And as Veronica presented, we can use different coupling functions. And to enable a representation of multiple regions of I activities, bumps, that represent multiple events, we use a coupling function with oscillatory decay. And while a Mexican head function, which has 2 zeros, does not generally support a stable solution of 2 or more regions of I activity, with an oscillatory function, which has infinite number of zeros, it is possible to generate stable multi-bump solutions. For example, here you can see in response to 2 localized bumps as input with different amplitudes, with meshing ahead, the response was only 1 bump, and with the oscillatory type function, 2 stable bumps coexist. If you consider now two sequential inputs localized close to each other, with Michigan head function, normally just one bump solution is generated, representing the first or the second input, depending on the input amplitudes. With oscillatory function in response to a stable localized inputs applied sequentially, we can obtain a stable two-bump solution. Depending also on the input width, the localized height activity converges to different stable states when the input is removed. For example, here, the input is small, as illustrated here in the first example, and when the input is removed, the activation present in the field converges to the stable resting state, that is the H value. In the second example here represented, we can see that in response to one bump, the activation converges to a two-bump solution. So to better understand how we can generate multi-bump solution in response to a sequential inputs, we studied the existence and stability of one and more bump solutions with and without external input. For example, if we use a coupling function that satisfies these conditions and an external input that satisfies these conditions, we can ensure the existence of one bump solution. A study of the conditions of the width and the relative distance of the external input was done in terms of the coupling functions to ensure a precise multi-item memory representation. So if we apply the sequential inputs, we can generate a representation of multi-item memory. To memorize and recall the serial order and relative timing of events, we propose the dynamic neural field model illustrated in this figure. And the model consists of a couple system of several dynamic neural fields, each one with a specific functionality. To understand the model, we can think about a concrete robotic experiment. Let's think about learning to play a piece of music on a keyboard in which each note is linked to a color. So the input is the color. And at the end of the sequence memory, we process the memory of order and the relative timing between the events are represented in the sequence memory field that you can see here in this figure, with strength of activation decreasing from element to element as a function of the elapsed time since the sequence onset. The activation gradient is established by a state and time-dependent dynamics of the value of H, the baseline level, by this differential equation. The on-decision field here in the sequence, when the sequence recall part receives the input from the on sequence memory as sub-threshold input, and during the sequence recall, the building up of the baseline in the on-decision field brings all subpopulation closer to the threshold, triggering the temporal sequence of bumps. The excitatory and the inhibitory connections between these two fields ensures that the excited bump representing the last decision becomes first stored in the working memory field and subsequently suppressed in the on-decision field. The wrapping dynamics of the baseline activity in the decision field is controlled by this differential equation. During recall, the speeds can be achieved by changing the value of the slope beta here in this equation, and we can recall the time in the same time that the robot learns the melody. If you are speaking about to learn a musical sequence. And here in this figure, we can see in the vertical lines the time that the music was played in the learning process. And here we see the activation in the recall field, and the time was the same that the melody was played by the human. And here in the second figure, we can see that the melody was played faster, but the relative time between the events was preserved. To better visualize the learning and the recall process, let's see this video where the robot learns a musical sequence, and after, for demonstrations, the robot plays correctly the melody. This is a part of the sequence learning, and now the recall. And now if you increase the value of beta, it is possible to reproduce the musical sequence faster. But the rhythm is preserved. Now in this second example, we can see is about handing over a task that the robot has to handing over a sequence of objects to the partner. And here in the first one, the partner is waiting for the object, but applying fast adaptation rules allows to adapt the timing, and in the it is too fast. In the trial 3, the robot starts his hard movement earlier and compensate the delay. And allowing a more fluent handing over. So in summary, the dynamic neural field model that I briefly show here can be applied to memorize the order and relative timing of observed events with repetitions, and subsequently recall information from memory with different execution speeds, preserving relative event timing, with flexible timing, because the event timing can be synchronized with external events, and can memorize and recall not only the order and relative times, but one extension of the model that I present here can also recall and memorize the duration of the events. Thank you for your attention.
Yeah, thank you, Flora. We are well in time. So again, if there is any question at the moment, or we use the time at the end of the session to ask more general questions concerning all talks or the general approach of dynamic neural fields. So if there are no questions, I mean, I would like to highlight, I mean, that the extension that Flora presented was really coming from the robotics side. So there was really questions from the engineers we are working with. I mean, how can you really store and recall very rapidly a sequence of events? Yeah, so it was really a need to extend the MARI model and introduce this oscillatory kernel as one possible solution. Okay, so if there are no...
May I just ask a short question?
Yes.
I just wanted to make sure that I got it right. If I understand the goal of this study is that by just changing one parameter of the Amari equation, we can get with the same external input different responses with different timings. Is this the point?
Not just one parameter.
More than
the parameters of the coupling function and the input functions should satisfy certain conditions to have the behavior that we want to get, or to generate, in this case, to generate multi-bump solutions.
Okay.
But with this mathematical analysis, you know that, okay, if these conditions are satisfied, we are able to generate the multi-bump solutions.
Okay.
I mean,
thank you.
I think the only where Flora changed one parameter was only when controlling the velocity of the recall. Then there's only one parameter that even you can argue in a biological way that there are some, yeah, I mean, you could implement this we have done this algorithmically here, but you could do it also in a more biological plausible way, but it's just one parameter that affects the slope of the increase of the activity.
Okay, thank you.
Okay, so then we can jump to the next speaker. Now, Tiago Sequeira will speak about numerical simulations of two-dimensional stochastic neural field equations with delays.
Yes, I need to share my screen, so I need to Flora to stop sharing her screen, please. Yes, thank you. So. Are you seeing the slides?
Yes.
Yes.
Good. So, hi everyone. Thank you for being here. My name is Tiago, and I'll present the numerical method and the results obtained in my master thesis, focused on delayed stochastic neural field equations. We'll start to introduce the neural field equation given by this expression, where omega is the domain of the equation, I is the external input, K describes the strength of the connections between two neurons, S is the firing rate function, and alpha is the constant decay rate. This model considers an infinite signal speed. However, this is not always a realistic assumption. Depending on the neuron type, we can have external velocities. Low has 1 meter per second. So to better mimic the neural behavior, we need to take into account the time spent by the stimulus from traveling from one neuron to another. So we introduce a delay term to the neural field, ending up with the delayed neural field equation. Many experiments in neuroscience suggest that neural interactions are in fact noisy. Motivated by this, Kuhn and Riedler studied the stochastic neural field equation with additive noise, which is the stochastic neural field equation. If we add a finite speed transmission to this model, we end up with this model that we will work with. Our analytical tools fall short when solving neural field equations. That's why numerical techniques are used to solve them. Yet, the computation of numerical solutions of these equations in an efficient way is still a challenge to overcome. When dealing with non-delayed neural fields, the integral operator can be viewed as a convolution. Then, more efficient methods can be used than the usual quadrature methods. However, when the velocity is finite, the integral term is not a convolutional anymore. Then, in 2013, Hutt and Rougier got around with this issue and provided a new efficient numerical method that addresses delay-dependent neural fields by rewriting the integral operator in a more suitable way. They used the Dirac's delta properties and made this substitution of variable. They wrote the integral operator A into a two-convolutional form, one in space and other in time. Then we can consider the integral operator as a Fourier transform. We'll talk about this later. Our goal is to derive a spectral method that combines the idea proposed by Hutt and Rougier for delayed neural fields and apply it to the stochastic scenario studied by Kuhn and Riedler. Thus, we consider the Carhuan-Loewe formula, which allows us to write V as an infinite orthonormal, as an infinite linear combination of orthonormal functions, where V hat are the function coefficients and phi are the eigenfunctions of the covariance operator of the key-winner process. Since the functions phi can be chosen, we just need to compute the coefficients V hat in order to obtain our solution V. For that purpose, we consider the following inner product definition, and we take the inner product between our equation and the basis function. And we obtain this expression here. Now we want to know how to compute each term of this expression. Kuhn and Riedler wrote this inner product as this expression, and due to the orthonormality of the inner product of these two inner products, we can write these two inner products as V hat. We end up with this expression. The next step is to choose the basis functions phi. Choosing phi to be the trigonometric functions, we can apply a Fourier transform to compute the inner products of the previous equation. Moreover, since we are dealing with real functions, the Hermite symmetry can be exploited, meaning that we only need to compute half of the Fourier spectrum. So, to compute V hat, we just need to derive the Fourier coefficients of I and A. Hutt and Rougier got around, they derived the Fourier coefficients of A hat of A and is given by this expression. And this inner product is just the Fourier coefficients of the input function. So, we write this equation, which is the equation that we want to discretize in order to derive our numerical method. So we begin to truncate our series in order to approximate V with a finite sum. Here, M and N are large integers, and larger these numbers are, the more accurate is the numerical solution. Next, we introduce an equidistant mesh with step delta x in order to subdivide omega into a finite number of intervals, and the same is done with respect to time. When dealing with a discrete domain, we have a finite number of delay rings. So, a finite number of delay rings. A hat, the discrete version of the Fourier coefficients of the integral operator is given by this expression. So applying the Euler-Maruyama scheme to our equation, we obtain this expression, and once we compute the coefficients V hat, We can now apply it to an inverse Fourier transform to compute our solution phi. About the convergence and complexity of this method, the method converges as a first order of convergence in space and time. And in practice, the inner products are computed using a fast Fourier transform algorithm, which means that we end up with this complexity, allowing us to save a large number of computations when comparing with the usual quadrature methods where the complexity is given by this. In this section, we'll show the simulations of some neural fields obtained with the numerical scheme presented. In every example studied, we consider the mean solution to be the mean of 100 trajectories, and we considered these two parameters. First, we test our numerical method to see if the method converges both in space and time. The problem on the left aims to test the convergence in space. Here is the analytical solution. And the problem on the right aims to test the convergence in time, where this exponential is the analytical solution to the problem. As you can see in these tables, the method converges both in space and time in agreement with the theory. The first example that we'll study is a 1D local excitatory and lateral inhibitory neural field. These fields models working memory mechanisms, which is a kind of memory that holds a response to a seized stimulus in a time scale of seconds. We can define it by writing these three functions, where the function input is active during the first second of the simulation and switched off after that. Also, we considered the initial condition to be 0. In the first two plots, with the input active, we see that the solutions, the delayed and non-delayed solution, responding to the stimulus. Also, we can see the effect of the delay. The delayed solution, the blue solid one, has a slower response to the stimulus than the non-delayed solution, which corresponds with the green dashed solution. In these two plots on the bottom, when the input is seized, the deterministic solutions retain the response to the input. As you can see, at t equals 5, we have a one bump solution. So my question is, if we add noise to the field, will the mean solution retain the same pattern registered? It depends on the epsilon. For epsilon equals to 0.01, we obtain the same qualitative profile, the one bump solution. But for epsilons equal or larger than 0.05, the answer is no. As you can see, at t equals 5, the solution has no longer a 1D bump profile, but multi-bump profiles. In the case of the non-delayed solution, we have 5 bump solutions after the seizure is seized, and in the case of the non-delayed solution, we have 3 bump solutions. So new bumps arise after the input is seized with this level of noise. Now we move our attention to a field present in the visual cortex of the monkeys. Mathematically, we can model it by using these 3 functions, and it is expected that this neural field exhibits hexagonal symmetry pattern. As you can see, with v equals 10, the solution takes longer to form the hexagonal pattern, while the solution with higher speed forms much quicker, being clear the effect of the noise in this field. The stochastic version of this field exhibits a rich repertoire of neuronal patterns. When considering epsilon equals to 0.01, the mean solution has analogous behavior to the deterministic one. As you can see in this figure, we still have the hexagonal pattern that the deterministic scenario exhibits. However, when increasing the noise level to 0.05, the evolution of the mean solution exhibits a different behavior. The solution starts to form the hexagonal pattern, as you can see here, at t equals 2.5, but slowly morphs to a striped pattern. At t equals 6, we have a striped pattern, and we no longer have any hexagonal symmetry. With epsilon equals 0.1, the noise is too strong that we only have random fluctuations, as you can see by this surface plot. Also, we can see that for the several epsilons, we have the different patterns. The last addressed neural field is a field where breather type instabilities were induced using only signal speed transmissions. So to model it, we use these three functions and consider these initial conditions. If we consider the non-delayed problem with the velocity with infinite velocity, the problem tends to the stationary state without oscillations. Here is the evolution of maximum and the minimum, and as you can see, the solution tends to equilibrium without any oscillations. However, this changes when considering finite speeds into the model. In these plots, we can see that the maximum and the minimum oscillate before the solutions tend to the stationary state. And as you can see, the slower the velocity, the longer the solution tends to the stationary state. With v equals 3, the solution tends to the equilibrium at t equals 60, while with v equals 5, it is much more quicker and reaches the equilibrium at t equals 20. These animations are the surface plots of the solution obtained with v equals 5 and v equals 3. As you can see, the solution obtained with v equals 5, it's already in the stationary state, while v equals 3 continues to oscillate. My question now is, what happens if if the velocity is lower than 3? With v equals 2, we obtain a solution that oscillates for all the time span considered, telling us that in the deterministic case, there is a bifurcation point somewhere between v equals 3 and v equals 2. As you can see, the solution never stops to oscillate in the time span considered. The next question is, will the addition of the noise affect the bifurcation point? The answer is yes, and according to this table, if you consider the deterministic scenario, the bifurcation point is somewhere between 2 and 3, while if we consider the epsilon equals to 0.001, the bifurcation point is between 5 and 6. The examples presented were simulated using a solver developed within the scope of my thesis and published in Julia's repository. This tool aims to fulfill the lack of a fast user-friendly solver to handle neural field equations. To download and install, just type this command in Julia's terminal, and to learn how to use the solver, please go to this link where there is a tutorial available. So summarizing the key results, when dealing with multi-bump solutions in 1D, if we add the noise strong enough, new bumps arise after the stimulus is ceased. In the field with hexagonal symmetry, according to different epsilons, the solution exhibits different behaviors. Regarding the breather type instabilities, we saw that the combined action between the delay and noise makes the bifurcation point to change. Also, Julia and the fast Fourier transforms proved to be a good combination to handle strong delayed scenarios. Although despite the benefits of this method, there is still room to improve. The first aspect is that the method doesn't deal with generic input functions. Currently, is only designed to work with stimuli whose maxima are fixed on the center of the domain. Phenomena such as traveling waves cannot be simulated with this scheme. Finally, the convergence in time and space could also be improved to obtain more accurate models. Thanks, everyone.
Yeah, thank you very much, Tiago. Again, we are well in time. Are there questions? I mean, I have one, but maybe others wish to ask as well something. If not, I'm really curious. I mean, in your example, the noise, yeah, the additive noise affected in your last example where the hop bifurcation takes place. So it shifts, let's say, the bifurcation point. There's a lot of discussion also in the community how noise affects, let's say, the memory mechanism. Let's say, just speaking about a single bump. Have you ever seen in your simulations that the bump drifts? Because we know that a bump is only marginally stable, so you can, by input or whether shift it along the axis. So have you ever seen in your many simulations something that the bump, a single bump starts to drift in 1D or 2D?
No, I didn't see the bumps drift. Of course, if you add noise, of course you have the random fluctuations, right? But the bump itself didn't move. I guess it was because the level of noise was not that high. But if I increase the noise just a little bit higher than 0.001, I just add noisy solutions without any bumps or without any pattern.
But in most of your simulations, you also used not the Mexican head, but for instance, this oscillatory kernel or with hexagonal symmetry. So it's not many simulations with just the Mexican head, or as a breather, yes, but
the breather, yes.
Yeah, but maybe okay. But it's really an open question in the field. Okay. I mean, how noise and which type of noise affects, let's say, or may shift the memory bump. So it was just for curiosity whether you have seen this in your simulations.
I think this is a good suggestion for future work. Actually, we can use Tiago's code to investigate this drift in the stochastic case.
Because it's highly efficient, the code, very fast. No? So I think it's really a good opportunity to use it for this specific question. Okay, there are no further questions, I think. So then I will go to the next speaker. Yeah, now the main speaker, who has 40 minutes time, Pedro Lima from IST. And he will speak about mathematical modeling of working memory in the presence of random disturbances using neural field equations.
Okay, so may I share my screen?
Yes.
Can you see my, I must do full screen. Let me. Yeah. Okay, so thank you for the introduction, and thank you. I would like also to thank all people who are listening to this talk. My talk tries to reflect the fruitful cooperation that was started about 4 years ago on neural field equations between the team in University of Minho, which is led by Professor Erlhagen, and the team at Técnico, where I am the leader, and I think this has been a very fruitful cooperation, because as you may have already seen in the talks, we have different kinds of contributions. The team in Minho is more focused on the robotic applications, and the team in Technic, to which I belong, and Tiago also belongs, is more focused on the aspects of numerical modeling. And in my talk, I tried to incorporate both these aspects, because this talk is the result of joint work which was submitted for publication, and this is this work was carried out in the frame of FCT project, the project Neural Field, and it has also the cooperation of Gennady Kulikov and Maria Kulikova, which are based at Instituto Superior Técnico. So my talk, as already said, is on the applications of the neural field equation to working memory. So it has many common aspects with the previous talks. So I will start with a short introduction, then I will introduce the deterministic neural field equation. Then I will try to highlight some aspects of the working memory process, and then I will turn to the stochastic equation, because one of the goals of this investigation was to study the effect of noise on the working memory process. A part of my talk will be dedicated to the numerical methods, and as usual, I will present some numerical results. Then I will finish with some conclusions of the work. So, according I think that for all the participants of the today's mini symposium, it's clear how complex it is to model the human brain. It's maybe the most complex system that science has tried to model, as it was already said in one of the previous talks. The nervous system contains about 10 to the 11 neurons, and these neurons are connected by about 10 to 15 synapses. Maybe it is it makes sense now to recall how a standard neuron is, what is the structure of a standard neuron. Every neuron has 3 parts. One of them is the dendrite, which has this form of a tree. It plays the role of an antenna. It's where the neuron receives the external signals. Then we have the nucleus, or the soma, which is the main part where the stimulus are processed, and then we have the axon. The axon works like a transmission cable. It's used by the neuron to send signals to the other neurons. So there are many different kinds of neurons, but all of them have in common this structure. And how do neurons communicate between themselves? As you know, the main quantity that we can measure in neurons is the membrane potential. It's an electrical measure, and if we look how the potential, membrane potential of a single neuron changes with time, we have this picture, a picture like this. So we see that from time there is what we call a spike, that is a moment where there is a sudden increase of the potential. In this moment we say that the neuron fires, that is, it's the moment when the neuron sends signals to other neurons. And as it was already mentioned in previous talks, one of the main parts of the human brain which is responsible by the main processes is the cerebral cortex. The cerebral cortex is the brain's outer layer of neural tissue, and in humans and other mammals, it plays a key role. It controls such processes as perception, awareness, thought, language, and also working memory, which we will speak about. It is only about 2 to 4 millimeters thick, but it contains only 1/5 of all the neurons in the nervous system. So this means that there is a very high concentration of neurons in the cortex. And another interesting fact is that according to recent it can store
Pedro?
100 terabytes. Speaking estimate. Okay, so about mathematical models, I will of course just mention some. Sorry. Can you hear me now?
It's better now. It was really hard to.
There was some interruption. I have to start the sharing again. I'm sorry.
Okay.
Can you see now my screen?
Yes.
Yes. So I started to speak about mathematical models. Okay, I will mention only some of the main mathematical models that have been used to describe the interaction between neurons. The first I want to mention is the model by Hodgkin and Huxley, which was introduced in 1952, and it was an important milestone in mathematical neuroscience because for the first time it was described the mechanism of ion currents and voltage changes in the neuron membrane. The mathematical description consists of a system of 4 ordinary differential equations. Then I would like also to mention the Fitzhugh-Nagumo equations, which were introduced in the 60s and that describe how the nervous stimuli propagate along the nervous system using the axons, okay? And finally, what is close to the subject of today's mini symposium, the neural field equations. They are they were introduced in the 70s, first by Wilson and Cohen, and then by Amari. In particular, in the previous talks, we were focused on the Amari equation, and what distinguishes the neural field models from other models describing the brain is that they treat the cortex as a continuous space, and they describe the spatio-temporal dynamics of the neural interactions. So what is, I'm trying to go to the following. Okay. So before going on, I would like to mention some applications of neural fields. One of the applications is in neuroscience and in medicine. Neural fields can be used for the interpretation of experimental data, such as data that come from electroencephalogram and from magnetic resonance. So it's a very important that we can integrate this data to, for example, to have diagnostics. So this is one important direction, and the other direction, which is close to the subject of our mini symposium, is the applications to robotics. Okay, it was already highlighted in the previous talks that neural fields are very useful to create new architectures of robots that can efficiently interact with humans. Okay, so once again, I present here the neural field equation in this version here with no delay, just the neural field equation which describes the interaction between neurons, neglecting the time needed for the propagation of stimulus. So here we are considering that the propagation speed is infinite. In this case, we have an integral differential equation where the unknown function is this function V, the membrane potential, which depends on the space coordinates here represented by X bar and on the time. And this is the unknown. We search for this unknown in a certain two-dimensional domain, omega. In this case, for the sake of simplicity, we consider the domain as a rectangle, but there are, of course, other possibilities. And what are the quantities that appear in this equation? I is very important. I is the external signal, so some stimulus that acts on the neurons. K is the so-called connectivity function. It describes the strength of the connection between neurons at space locations X bar and Y bar. So in this model, we assume that the connectivity depends only on distance. This is not always the case. There are more sophisticated models which take into consideration not only the distance but the specific location of each neuron, but in our case we will do this simplification. We assume that the connectivity depends only on distance, and S is the firing rate function, which was already mentioned today. The firing rate function is very important because it reflects how the neuron reacts to the how the capacity, the firing capacity of the neuron depends on its potential. So typically, if the potential V is under a certain threshold, the neuron does not fire, and it starts to fire when the V is above this threshold. So the simplest case of the firing rate function S is the Heaviside function, but we have also more sophisticated models where S is a sigmoidal function, where S may take more than 2 values. It can change continuously from 0 to 1. Okay. Finally, there is also this constant alpha, which we call the decay rate. So if there were no external stimulus and no interaction between neurons, the potential would naturally tend to 0, and alpha reflects how the potential would decay to 0 in this case. So now I said that our aim is to use the neural field equation to describe working memory. I try now to explain how this happens. First of all, working memory is the capacity of neurons to transiently hold sensory information to guide forthcoming action. For example, when we are observing an object that is moving, and at a certain moment this object cannot be seen because it is covered by an obstacle. Thanks to working memory, we keep the information about the location of this object, and we can, in certain in a certain measure, to predict where it will appear again. This is, I think, one example for how working memory acts. But as you have seen from previous talks, it has many other applications. So to model this process mathematically with the help of neural fields, what we have external inputs of a certain kind. Here in this picture on the left side, we have an example of an external input which consists of 2 bumps. There is we have, for example, if it is a light signal, it will be a light signal of 2 colors. Okay. The graphic is 2D because here one of the dimensions is the time. So what this graph on the left shows is that after a certain time, the external stimulus ceases. Okay, it is interrupted. For example, a light which is blinking, and in the right-hand side, what we can see? In the right-hand side, we can see the response, the solution of the neural field equation. So at t equals 0 in the starting moment of time, the response is 0, so the field is not active. And then in the first moments, what we see is that the response is growing, and it is growing in response to the stimulus, okay? So the parts of the field which are active are the ones which receive the excitation from the external input. And then what is interesting for us is that when the external input ceases at this moment of time, what happens with the solution? The solution decreases, but it does not go to zero. The solution tends to a certain stationary solution, different from zero, and in this case it's a two-bump solution, and this two-bump solution keeps the information about the external input. So this is what I think is the key point of the working memory process. Yes, that is a mechanism that allows the information about the external input to remain when the external input itself has disappeared. Now we see one example of this process here. Our graphic is 1D, so in this case the graphic does not represent the time. We have an example where we have a light signal, so the variable, the independent variable here is the color. As you see, as the independent variable varies from 0 to 360, we have different colors. So what is represented in this graphic? In dashed line, we have the input. So we can see that the input in this case is a blue signal, okay, because it is concentrated in the blue zone of the variable. And we see also that this input is over the threshold. The threshold here is represented by the red dashed line. So once the input, the external input is over the threshold, it means that it can excite the neurons so that they start to interact with each other, okay? And when the neurons start to interact with each other, some activity is generated, and this activity generates this bump, which is represented by the full the bloom line. We have this form. So here. Introduced in this work in the 2D neural field. Our goal is not just to represent the nature
Pedro, there's again problems with the connection, I guess.
There was. Can you see now? Now?
No.
Can you hear me?
Yeah, yeah, again, yeah. We can hear you again, yes.
Okay, sorry. Maybe there is some problem with my internet connection. Okay, I have to share the screen with you again. Can you see my screen now?
Yes, we can see.
Yeah, okay, let's hope that it will work now. I started to speak about 2D neural fields. What I wanted to say is that in this case, we want not only to register the nature of a certain external signal, for example, the color of a sign, but we want also to register the moment when it happened and the duration. So we introduce the second variable, which here is the variable x, and it represents the time of the event. So using this representation, for example, a signal with one light is given by this ridge here, with extends on time, and a signal which consists of two colors that consists of two colors will have this form here. This is the external signal. Okay, now let me move to the next slide. Okay, so our goal is that the solution of the neural field equation will reflect a sequence of signals in such fashion that we will have the information about the sequence of the signals, how many signals there were, and what was the form of each signal. So this is mathematically, this is achieved by combining the external input with a traveling wave, which is represented here. Traveling wave is moving in the direction x, which, as I said, is the direction representing time. So what happens is that the traveling wave will intersect the external input representing, for example, a certain color at a certain moment, and then in the place of the intersection of the two graphics, a bump arises, okay? This bump here. And what is interesting is that the coordinates of the bump represent from one side the color of the external signal, and from the other side the moment when it happened. So this bump will keep both information about the nature of the signal and the moment and the duration of the signal. Okay. Now, in my talk, I will, as in Tiago's talk, we will take into account random effects. Because why these random effects are important? Some sources of noise in neural fields are the irregularity of spikes, the non-homogeneous or irregular connectivity, and the perturbation of external stimulus. This is all significant because, as you can understand, in mathematical models, we always assume that, for example, the connectivity has the form of a continuous, smooth function, but we understand that in reality is not exactly, happen exactly this way. So it's important to take into account the possible deviations which are caused by random factors. And what questions we would like to answer by means of stochastic models. For example, does noise interfere in the existence of stationary solutions? From Tiago's talk, I think we have already understood that it may indeed interfere, okay? And how far the stationary solutions can be modified as a result of noise. For example, may a stationary solution be transformed into another just as the result of noise, and what is the probability that this happens? So this are the kind of questions that we want to answer when we use the stochastic neural field equation. Now, what is the form of the stochastic neural field equation? Here we follow an investigation by Kuhn and Riedler from 2014, which was already cited by Tiago. In this work, the authors introduced this stochastic neural field equation with additive noise. So the stochastic term depends on epsilon. So epsilon here can be interpreted as the strength of the level of the noise, and the noise itself is represented by WT, which is a Q-Wiener process. I note that in this case we have a partial stochastic equation. So at each we have a family of stochastic processes, one stochastic process for each value of the variable x. And we want to do a numerical approximation of this equation. This numerical approximation is based on the Karhunen-Loewe formula, which allows us to expand a stochastic process as a series of this form. Sorry. We have this expansion, so we look for the solution UT in this form, and to obtain the coefficients UKL of t of this expansion, we have to solve a system of equations. Okay, so how do we obtain this system? We use the fact that the stochastic processes VKLX are form an orthogonal system. And then we multiply both sides of the stochastic neural field equation by we do the scalar product by the orthogonal functions of the basis. What concerns the stochastic term, it can also be expanded as a series of this form where beta kappa L are some stochastic processes. So we have to assume that there is a certain correlation between the stochastic process corresponding to points x and y. The correlation is given by this expression. So using all these facts, we obtain a system of stochastic differential equations. By now, it is a system with an infinite number of equations. We have one equation for each coefficient UKL of the expansion. And of course, when we want to solve this numerically, we cannot consider the infinite series, so we have to truncate the series and to use what is usually called the Galerkin method. So we look for approximate solution UN, which is obtained by truncating the series. So we consider n plus 1 squared terms of the series, as much as the number of function basis functions we are considering. And to obtain now the coefficients UKLT, we have now a finite system of nonlinear equations, and each of these nonlinear equations, of course, is also a stochastic equation, and we will use now certain methods to discretize this equation. I will not go into details here, but I will say there is a difference with the method described by Tiago, because in the method described by Tiago, we made use of the fast Fourier transform to accelerate the process. But here this is not possible because, as Tiago said, the method he was using is applicable in the case when the external input and the solution has spherical symmetry, and here we don't have this because of the traveling waves. So we are not using the fast Fourier transform, but we are using a rectangular row to approximate the integrals. This means that we introduce a mesh with step size h, both in the x and in the y variable, and we assume that the number of mesh points in both directions is much greater than n, where n is the number of basis functions. Okay, so now here we represent how the inner products can be computed. They are computed as sums, because these sums are the approximations of the integrals by the rectangular rule. And how do you do the time discretization? In Tiago's work, the time discretization was done just by introducing the Euler-Maruyama method, which, as you maybe know, is the natural extension of the Euler method to stochastic equations. In this work, we have carried out two types of time discretization. The first one by the Euler-Maruyama method, which has only strong convergence order of 0.5. And then we have also used another time discretization of a higher order, the so-called Ito-Tyler method, which has convergence order, strong convergence order 1.5. As you see, the technical details of the Ito-Tyler method, as one could expect it, are more sophisticated. I will not go here into details, but I want to underline that it is very important to have two methods of different order, because in this way we can control the error. Okay, we can compare the results obtained by the low order method with the results obtained by the higher order method, and in this way we have estimate of the error of lower order method. Okay, so how much? 35 minutes. Okay, so these are, I will skip the details about the Ito-Taylor method. I will now just remember that we are using as basis functions trigonometric functions, more precisely cosinus. Okay. So our discretization is based on these basis functions. And now I will continue with some numerical results obtained by this numerical method. We are using here the connectivity function, which was already described in previous examples, that is oscillatory connectivity function, as it was already remarked by Professor Wolfram Erlangen. This connectivity function is very important because it allows that we have multi-bump solutions of the equations reflecting the external inputs. And in this numerical example so far, we have only we have always used these values of the parameters, A, which is the amplitude of always 0.06 equals to 1, and as firing rate we are using the Heaviside function with threshold B. Okay, so in our examples, B will be equal to 0.1. So some technical details. Our domain, special domain, is square, in this case minus 2020 by minus 2020, but I would like to mention that we always represent the results in the positive part of the x-axis, because the x-axis represents the time, and the time has physical meaning only when it is positive. Okay, so we use as step size in space h equals 0.04, step size in time ht equals 0.1, and 51 basis functions. The initial condition is always the zero function, and in the case of the stochastic equation, we perform the computations with 100 passes. Okay, so when I speak about the mean solution, is the mean of 100 different realizations of the stochastic process. Now I will describe 4 numerical examples corresponding to different sequence of external stimulus. The first example is the simplest one. Here the external stimulus consists only of one light signal. This one light signal is active, one color signal is active during the time interval from 0 to 1.5, and then it ceases. And we want to know what is the response of the neural field equation to this stimulus. Of course, we have also I0. I0 is the traveling wave, which, as I said, is only always present in these problems we are considering, because it allows us to represent the time. So what we see, the bump which has the direction of the y-axis is the traveling wave. It is moving along the x-axis, and the other bump represents the one color light. In the place where the two bumps intersect, we have this bump representing the external signal. So with time, both the traveling wave and this initial bump disappear, and what remains is one only bump, whose coordinates represent the color of the signal and the moment when it happened. So in this case, we have only one bump because there was only one color signal. Okay. Now, in the next slide, what we see is the effect of noise in the response. On the left-hand side graphic, we have the case of weak noise when epsilon is equals 0.04. So here we see that noise does not have a very strong influence. In the right-hand side, we have the case of strong noise with epsilon equals 0.08. Here the effect is noise is more visible, but still what is important that this, in any case, we have only one bump. Okay. Solution consists of suprathreshold activity. So in this sense, the noise does not disturb the memory about the external signal. Now, in example 2, we have a more complicated case. Here we have one signal with two colors. The different colors are represented by the stimulus I1 and I2, which both these stimuli are present in the time interval from 0 to 1, and then they cease. Okay, and again we have the traveling wave represented by I0. So before going into the physical description of the results, I would like to mention that we made also some tests about the accuracy of the method, and we in this case, since we don't know the exact solution, how we control the error? We control the error by comparing the low order method with the high order one. So here we have the error norms for different step sizes, and as it could be expected in the deterministic case, so this table here is for the deterministic case, we have convergence order 1. Okay. Now, in the case of, in the stochastic case with the noise level epsilon equals 0.04, here, of course, the convergence is slower. Remember that here we are comparing the average, the mean solutions, okay, the average of all the stochastic passes. But anyway, in both norms, we see that the error norm is decreasing and tending to zero as the step size in time decreases. Okay, so we made this test to check the accuracy of the method. And now the graphics of the results. As I said, in this case, we had also a signal in a certain time interval, which consists of two colors. So the in the first moment of time, when t equals 1 on the left-hand side, we can see still the ridges representing the external input with two different colors. Then after some time, the external input disappears, and at t equals 5, we have this picture on the right-hand side, which is already close to the stationary solution. And as it could be expected in the stationary solution, we have two bumps, okay, which represent the two colors of the external signal. Now, the effect of noise on this, in this case, is visible in these graphics. Again, we have a graphic for the case of weak noise epsilon equals 0.04 in the left-hand side. In the right-hand side, epsilon equals 0.08. And again, the main conclusion is that though the noise affects the solution, but it does not change its main features. So again, the stationary solution has two activity zones, two bumps, which reflects the external signal. Now, third example, what we have now. Now we have a sequence of external signals. The first series of signals is active in the time interval from 0 to 1. Here we have a signal with two colors, which are represented here by the I1 functions I1 and I2. Then in the time interval from 1 to 5, we don't have external signals, only the traveling wave. And then from in the time interval from 5 to 6, we have again two signals which are similar to the first series. I3 and I4 have the same location as I1 and I2, but they just happen at a later moment of time. And we want to see how this sequence of signals is reflected in the output of the neural field equation. So in this graph here, we have, in this series of graphs, we have three graphs representing three different moments of time. In time t equals 1, we have the first, the solution reflects the first series of signals with two colors. And then at time t equals 6, we see that a new series of two bumps is appearing that correspond to the second series of external signals, okay? And here at t equal 5, at moment t equals 5, we see already that we have 4 bumps. Okay, 2 bumps corresponding to the first 2 signals, and 2 bumps corresponding to the last 2 ones. Now, the effect of noise in the case of this example. First, at moment at the first moment, when at t equals 1, we see the external the external input in the case of the weak noise, it's very close to the deterministic case. And in the case of strong noise, we see some perturbations, but again, we have only 2 bumps. In moment t equals 6, again, with the weak noise case. This is at the time t equals 6. And now look what happens at the time t equals 8. In the case of a strong noise, besides the 4 bumps which reflect the external input, we have 2 more bumps. These 2 bumps are just the result of noise. So they are like false memories that occur as the effect of noise. So this is this shows something that was also present in Tiago's work, that the noise can deform the solutions of the stochastic narrow field equations, not just cause some perturbation, but it may cause a different type of solution, like in this case, a solution with more bumps, which represent false memories. This was an interesting finding obtained in these numerical examples. Here we have the same graphs, but now we see just the level curves of the graph. So in the right hand side, we have the case of weak noise. In this case, we see clearly that there are only 4 bumps. In the case of strong noise, we have 2 more bumps appearing here. And we can ask, why do the false memories appear exactly in this place here? We should say that these bumps appear in the places where the noise together with the connectivity are strong enough to cause suprathreshold activity. Okay, so there is we can see that this place here corresponds to a peak of the connectivity function if the connectivity function is centered at the closest bump. So this false memory here arises as the effect of noise, but it arises in the place where the connectivity is stronger, so it's more likely to create this activity. Okay, and finally, I don't know if I have already past my time, Wolfram.
Yes, in principle, yes. I mean, I don't know whether you can skip the last example, or you want to
okay,
finish?
just I would say that in the last example, we have also a series of inputs, but here the first input consists only of one color, and the second series of inputs consists of two colors. So we have at all 3 bumps. And here again, we have false memories. I say, let me just show this last signal. You see, here again, we have bumps that appear just as the result of noise. They do not exist in the external signal. So this is also an example of false memories. Okay, and here are the level curves for this example. So now I can go to the conclusions. We have described the two-dimensional neural field model, which explains how a population of cortical neurons may encode in its self-sustained firing pattern simultaneously the nature and time of sequential stimulus events. The postulated wave mechanism explains how a nervous system lacking specific sensors for temporal perception may develop neurons that respond to specific interval durations. The numerical results presented support the conjecture that if the external input has appropriate intensity and duration, and if the connection kernel is of the oscillatory type described here, the neural activity can generate stable multi-bump solutions which contain the information carried by the external signal. And now, in the case of weak noise, the structure of the stationary solution is preserved in the sense that the mean solution of the stochastic equation has the same number of bumps as the solution of the deterministic equation, but in the case of strong noise, the structure of the stationary solutions can be significantly changed, indicating that the information carried by the external stimulus can be deformed. So this is all. Thank you for your attention, and I'm sorry for exceeding my my time, but there were also some perturbations with the connection. So excuse me for.
Okay, Pedro, thank you very much for the interesting talk. And for the clear conclusions here on the last slides. I think it's also interesting for the audience, your introductory remarks about the complexity of trying to model brain functions or neural activity, just given the incredible number of neurons that exist in connections. So one might wonder whether this very simplified equation, let's say, may capture something about really what's going on in the brain. But I can say, I'm doing this now for several years, that we have used actually these equations or this type of equations to really model neural activity recorded in the brain. So it's impossible. The advantage is that it's possible to describe some key characteristics of neural population activity, and at the same time you can do it using mathematical tools. That is, I think, the big advantage about over let's say neural network modeling, which is now very, very famous, and a lot of people addressing this. So I said this, is there a specific question here at the moment for this last talk, or some general comment or whatever? I mean, there is any questions, any comments? Yeah, I mean, this was just an obviously in 2 hours, just not possible to cover.
I think there is someone who wants to, in the chat, there is someone who wants to make a question.
Filomena Diaz de Almeida has the hands up, but I don't know.
I don't know whether we can listen to Filomena or just in the chat. Let's see. There is in the chat.
No, in the chat there's nothing. I don't see it. I mean, I obviously have a lot of specific questions which might be not as interesting for the general audience here. And we obviously continue to discuss aspects here. My question now, just one short one, because you cannot use or could not use fast Fourier transformation. So just give me an idea. We have seen in Thiago's talk, there was a 2D simulation of a 2D field in real time, let's say in seconds. So how long does it take a single run in a 2D simulation in your case here? Really in
also a question of seconds. It is not, it's longer than in I don't have now the figures here, but I have it's Kulikov who has done this simulation, the code and the simulations, and he told me it's anyway longer than in Thiago's case, but anyway fast, because we can make use of certain features. In this case, the code is in MATLAB. We can make use of certain features of MATLAB. For example, we just compute the matrix representing the connectivity once in the beginning. Whereas this big matrix is computed one time, and at each time step we don't have to compute it again. So there are some how to say some tricks that allow us that the computation does not take so long as it could be. But of course it would be interesting, and this is an open question, whether we can anyway to exploit the fast Fourier transform. Maybe there is some way, it's an open question, of transforming also this the equation in this case, so that we can use again the fast Fourier transform. By now it's still an open question.
Okay, I mean, we are just in time. It's 12 o'clock. I think I have to finish now officially the session. So it was an opportunity to introduce some aspects of mathematical neuroscience, and I hope at least for some of the audience it was interesting, and maybe someone of you wants to dig deeper and learn more about mathematical neuroscience. It's a very interesting and very challenging domain, and I think we will hear about it in the future for sure. Yeah? Trying to model some brain function, and in our case, we try to use it to make robots more intelligent. Okay, then thank you very much for listening to the talks. Thank you very much for all the presenters of interesting